All right, welcome to our session. Can everybody hear me okay in the back? All good? All right, happy International Women's Day. Yeah? Thank you, ladies, everybody that's in the crowd. We have Suzanne here with me as well. I'm Mollenkopf. I'm the real-time and the big data capability lead for the ArcGIS platform. And Suzanne is here with me as well. She works on the team and helps us stress it out to massive scales. What we're going to be focusing on now in this session is talking about today's state of affairs and where real-time and big data GIS is today with the ArcGIS platform. We'll also talk about the emergence of a new class of problem that we're seeing in the industry. And then we'll talk about some R&D efforts that we have underway to address this. These R&D efforts will likely form into a product that will be released in the future, as well as next generation architecture for GeoEvent, GeoAnalytics, the big data store, all the other things that are part of our ecosystem that we have today. So this is kind of an early glimpse into some of the work that we're doing. We're working with some early adopters in this space as well that have some pretty high velocity and high volume data that we're verifying all of this with. And then we'll talk about some of our first steps or next steps of where we're going to take this first. Our project that we have named for this, everything before it becomes a product is always a project name within Esri. So this project is called Trinity. It's Trinity because of bringing together the massive velocity of real-time GIS, the massive volume of big data storage, and then also the analytic capabilities of GeoAnalytics, and bringing those together, exposing it all as a ArcGIS Enterprise that you can work with just like you would work with any normal portal. But underneath that is, the capability to scale out to hundreds or thousands of nodes to run these computation on, and also to store this data. So the current state today is that we have actually a really good offering today for the scale that a lot of folks need. And so we have our offering includes an ArcGIS Enterprise that can have added capability added to it through GeoEvent Server being the real-time aspect of our platform, bringing data in and ingesting that from real-time streams. We have a spatial temporal big data store that's been in the platform since the 10.4 release. And this allows you to have a geodatabase that's scaled across multiple machines. So you can have extremely high volumes of data stored across this. It does some really interesting indexing to allow really quick access to the spatial data, the temporal data, as well as all the other attributes that are in the store as well. So basically you can think about it as a time series database that we've added a bunch of geographic capability to, but it allows you to play things back very quickly and at very large scales. The other aspect of that is a map and a feature service within ArcGIS Enterprise that, when it's working with the big data store, allows you to aggregate data on the fly. So instead of running an aggregate tool, you can simply connect to the data that you're interested in. It'll aggregate that data on the fly into geohashes, into squares, into hexagons, however you want to see those. And this is very useful, especially when you're dealing with millions or hundreds of millions of observations, where you don't want to render that many things on the client. On the right side, new at the 10.5 release is a functional server that's part of ArcGIS Enterprise that's focused on allowing us to do parallel computation on the data that's stored in the big data store, as well as on data that's external, which could be in like HDFS or Hive or other systems of that nature. And GeoAnalytics Server is our answer for that, and this allows you to perform analysis much faster than you could before, or things that weren't tenable are now possible with GeoAnalytics Server. A minimum environment for this includes about 4 machines. So you typically want to have these in an isolated space. This is a best practice that we've experienced over time after fielding many of these into the field for customers. And your ArcGIS Enterprise typically should be isolated to only doing its function. The GeoEvent server and the GeoAnalytics server, depending on how high stress that you have those machines, need to be in an isolated environment as well. So when you run a GeoAnalytics job, it's going to basically consume all the CPU and as much RAM as it can consume. So if you were to put that on the same machine as GeoEvent that's continuously streaming in data, that's also using CPU and RAM, it's going to contend for those resources, and you're going to have non-deterministic results if you put those on the same machine. So it's really really a best practice to put those in an isolated environment. And then also the spatial temporal big data store node or nodes that you deploy in here also are very I/O and RAM intensive. RAM intensive in that if you access data in the big data store, it'll actually make its best effort to keep the hot data that you've accessed most recently in RAM, so that when you access that data again, it doesn't have to go all the way back to the disk. So this is the minimum environment to kind of get started. You certainly can install all of these on one machine. Lots of us do that at Esri for development testing and staging and things of that nature. But when you move to a production system, it's mostly ideal to isolate these out into their own environment. While that's the minimal requirement, we actually recommend an environment that looks more like this. And the main reason for that is to have redundancy on your data inside the big data store. So if you only have one node in the big data store, you don't have any replicas of that data. So if the disk or that node fails for some reason, then your only recovery point is a snapshot that is taken on a daily basis with that. So if that's good enough for you, you certainly can do that, but a lot of our customers require better availability of their data for that. So we suggest at least a 3-node cluster for that, and that allows us to write replicas to other nodes in the cluster. And if one disk fails, the ones that had the replicas would take over as the primaries, and the data's not lost. And so there's no interruption of data or anything else, and all of that's transparent. You don't have to do anything, it just works inside the spatial temporal data store. On the geoanalytics server, as far as picking the right number of those, typically a good place to start is to at least, if you're going to be working with the spatial temporal big data store most often, at least to have one in parity with each node that you would have on the big data store. Certainly you can go more than that as well, but if you want to get as much parallel computation as possible, working with the data that's distributed is going to be much more efficient if you have the right number of parallel computations happening across that. There's some deeper dive sessions into those topics. There's a best practice session tomorrow. There's a geoanalytics session tomorrow as well if you want to learn more about those details. There's also a session on the big data store that will go into depth into those topics. But this is kind of what we recommend, and so this is kind of an interesting thing to set up because you have to set up lots of machines, and then when 10.5.1 comes out, there's an upgrade path that you have to go through to install 10.5.1, and so it becomes a bit to manage. So there's also an emergence of a new class of problem, and the new class of problem is that with this advent of IoT sensors flooding the network of data, trying to bring all of these into an ArcGIS system or a GIS system of record becomes a bit challenging. So it's not necessarily that there's one feed that's really high velocity. Some of our customers actually do have that problem, but it's a combination of all these feeds that people want to do. So if we're creating a smart city for a local government or a state, these are all the things that they would be interested to bring in. And so all of this adds up to be high velocity data, and our on-premise software currently today can only scale to a certain fashion. So this leads us into the need for having the ability to scale out at massive levels. And so we're seeing customers that need to have lots of geo events, lots of geoanalytics, lots of big data store nodes because they want to keep the data around forever. So if they want to do that, they have to continuously add more big data store nodes to satisfy the volume of storage that they require for that. So this is what we're seeing is, even tens or even thousands of machines are starting to be required for some of these customers. And it's not really practical to take our software that we have today and deploy it in that type of fashion because it would be a management challenge to try to manage all those environments. So what we've done, and this is where kind of the R&D starts, is we've come up with a next-gen architecture for how to handle real-time and big data. This will be offered in a number of capacities that we'll go through here. First, what I want to do is kind of describe the concept of it. And the concept is very similar to our real-time GIS and big data story that we've been telling all along with GeoEvent and geoanalytics. It's just at a different scale. So if I have a customer that has 200 events per second, like you might have saw on the plenary stage yesterday with real-time flights coming in for North America, we can certainly handle that with our software that we have today. But we're getting customers that want to track 1.5 million vehicles every second. And so how do we actually get to that scale where we want to track vehicles, or we want to track people, or we want to track other things, and there's such a quantity of them and the frequency of updates are so fast? So Project Trinity is about bringing these things all together and giving us a new operating environment to actually operate these services inside of this environment. And so we're moving to, how do we do millions of events per second, and how do we quickly visualize and replay billions of features, which is not uncommon these days. And then also, how do we perform fast analytics on these observations once they're put at rest inside of the spatial temporal data store. So this is the same story as what we tell today with real-time and big data, and it works with moving things. So these are the planes and trains and other things that move and emit a different GPS location periodically. But it also works with stationary things. So these could be environmental sensors of air quality or water levels, water gauges or things of that nature, where they don't necessarily move, but their attribution changes all the time. And so we have customers that need to integrate all of those, so all of the above is typically the answer. And so from an IoT perspective, all of the above are applicable there, and we need to satisfy all of those use cases. So at the highest level concept of what Project Trinity is, it's taking a customer's problem and decomposing it into what are you trying to do. So we want to be able to bring in data very fast. We also want to be able to run analytics on that data that's stored very fast. And depending on the data retention cycles and the other factors in here, we would apply some functions to basically capacity plan an environment for a customer. And so this is just a hypothetical scenario. Not every Trinity user would need this type of environment, but this is just a hypothetical scenario of maybe I need to track 1 million events per second, and we know how many events per second each of our real-time analytics tasks and our sources can handle. And so what we would equate to is that you need to have 80 nodes for this particular customer. And so we don't want to manage 80 nodes for that customer. What we want to do is actually treat that as one big operating system and say, you know what? It's not 80 nodes, and we'll never think about it as 80 nodes again. We're going to think about it as 880 cores, 3 terabytes of memory, and 50 terabytes of storage. And it just looks like to us one big operating system. And so we're resting on the shoulders of giants that have already solved these problems before. We're not inventing a technology framework to do that. And so what we're using for this is Apache Mesos and DCOS, which is a data center operating system. And it's exactly the premise of data center operating system to treat a whole pool of machines as one operating system, where I can schedule work to run on that operating system. So I don't really care where it gets placed, which node it gets placed, or where it runs. I just want it to run. Just like when you open Outlook on your machine, you don't really tell it what core to pen to. So it's the same concept here, and we're resting on the shoulder of giants because if you've ever used Siri before, you're hitting an 80,000 node cluster that's running on DCOS. If you've ever called an Uber car before, you're resting on, they're using the same type of infrastructure as well. You ever bookmark your Netflix movie that you're watching? It's based on Apache Mesos and DCOS as well. So we're not inventing a framework here, we're leveraging a framework that's already proven in the industry, and we're applying our software to make it run inside of this environment. So what this is we decompose the aspects of what we have for GeoEvent server, for GeoAnalytics server, for ArcGIS server, and we run small microservices, if you want to call them that. And these microservices run inside this environment, and I can scale them up, I can scale them out inside of this environment. So what we can do is we can schedule work to run on these in this environment. So I can run an ArcGIS Enterprise, which will be my portal and my relational data store and my hosting server. And I can run this inside of this environment. And guess what? Also, this operating system knows that if something's supposed to be running and it fails, it'll actually restart it on another node, or it will take other action depending on how we configure it to work. So we don't necessarily need to run simultaneous ArcGIS Enterprises just to have high availability, because our operating system gives us that high availability. So if we're willing to take a few seconds downtime, then we could just let it spin up somewhere else, or we could certainly run more than one. And if any one of those fails, it would spin it up on another machine. What we also want to do is very quickly be able to establish our spatial temporal big data store. How many of you are using the spatial temporal big data store either at 10.4 or 10.5? A few of you. So how long did it take you to set up that environment? How long does it take you to install the big data store? No comments? How long? Too long, okay, great answer. All right, so our premise is here is that we can actually run these very quickly and establish a cluster very fast. So if you were to do this by hand today with 10.5 on-premise software, you would physically go into each one of these machines, run an ArcGIS data installer, choose the Spatial Temporal data store, put a URL into your ArcGIS Enterprise, and then it would register with that. And then you would go through that process 30 times to have a 30-node cluster. So that would take you a bit of time to do that. We can do that in a 30-node. We can spin up a 30-node Elasticsearch cluster. It takes about 47 seconds. The reason why we can do this is because we're using containerization technology. So we have Docker images, we have other types of container images where we deploy these containers out into this environment. So what we tell this big operating system is, I want to run 30 of this Docker image, and it goes and spins that up. And we already have the Docker image inside this environment, so it doesn't have to download it. It doesn't take any time to do that. We just basically create instances of that, and we have a 30-node big data store cluster in less than a minute. And so that's great for us, and we'll actually show you some of this in a demo in a bit. The other thing that we want to do is to be able to run batch analysis. So this is the equivalent of running like a geoanalytics job. So I don't necessarily want to have a geoanalytics server running in this environment because I don't want to have things that just sit there idle until there's work to do. I want to just spin up resources when I actually needed to do work. So this is, if you watched the keynote this morning about the serverless approach or the functions or those types of things, where whenever we get a geoanalytics job, we spin up resources to run those. And when there's not, we have blue boxes there where there's available cores, available RAM, and other things. And so when we run a geoanalytics job, it runs, and we can also co-locate it on the same node as where the data is as well, so that we can get super fast performance on the analytics that are performing. So we're sending the program down to the data. One aspect of geo event and us decomposing that into this environment is that geo event fundamentally is three main things. It's bringing data in or ingesting data, what we call a source here in this case. It's also taking those events that come in and routing them to all the different geo event services that have an interest in those events. So I might have 5 geo event services that are consuming the same feed to do different analysis. And so we have this thing called a hub that basically sits in between the inputs in geo event and the geo event services, or in this case, the sources and the real-time analytics. And so this hub is responsible for sending events around. And so if the geo event services can't keep up as fast as the data streaming in, these hubs start to accumulate data, and then we eventually, pull off all the data without losing data. And so that's the concept of what a hub is. And so these hubs can also run in this environment. Again, we're using the shoulders of giants here. We're using Kafka, other industry standard technologies to do this. We're not inventing our own messaging system. We're leveraging what's working in the big data space. The other fundamental difference here is that we want to be able to scale out really quickly and really easily. And so what happens today in a geo event server is when we go to a customer site, we might see that they have 30 geo event services that are configured and 15 inputs. All of those inputs and geo event services today are running on one node that's all contending for the same CPU, the same RAM, the same everything else. And so when we get to a customer site and they're like, you told us this did 3,000 events per second, but they have 50 geo event services deployed, they're seeing a couple hundred events per second. The reason is the contention of resources that are happening there. And so what our premise was in Trinity here is to actually run a geo event service, or what we're calling a real-time analytic task in here, but actually be able to say, run that geo event service, but I want to isolate resources just to that real-time analytic. So you get 4 cores and you get 8 gig of RAM. Nobody else can deal with that. So that's yours. Nobody else can contend for those resources. And by the way, I want 20 of you to run. And so what we have here is, instead of 20 geo event servers running with lots of things contending, we're running one geo event service where there's 20 of them running on different machines, but we're scaling this out. So this is what allows us to do, hundreds of thousands or millions of events per second, and scaling it out this way. And by the way, we've also written those real-time analytic tasks using Spark and some of the other techniques that we're doing, again, resting on the shoulder of giants here. Then we can also deploy other real-time analytic tasks, and then, so this might be what a cluster looks like once we have some real-time action going on, as well as the batch analytics, the green that are happening down below. And then the last thing that would get provisioned to this Trinity environment are the things that actually bring in the data from the sensors that are out in the field. So these are what we call sources. It's a source of data, a source of streaming data that's coming in. And those sources, again, can be scaled out as big or as small as you need them to be. Does that make sense at a concept level? Yep. Okay. So what we're going to do now is I'm going to kind of introduce an end-to-end workflow demo that Suzanne's going to walk us through, and we'll show you a sneak peek, early glimpse into some R&D work that we're doing to provide this environment. So this is a dashboard that we provide inside of Trinity, and it basically gives you a view of your operating system, the thing I was describing before. So for this particular operating system, we have 264 cores, we've got 1 terabyte of RAM, and we've got 30 terabytes of disk space. And there just happens to be 33 connected nodes, but that's not really important. We don't really care about the number of nodes. So to create this environment, it takes about 13 minutes. So 3 minutes of that is provisioning the environment. It doesn't matter if we're on Azure or Amazon. We can spin it up in the same amount of time. Even if you wanted to do it on premise, it takes about the same amount of time as well. So assuming you have machines and hardware ready to go with the prerequisites in place, it takes about 3 minutes to provision the machines. To get the installers and all the Docker images and all of those things onto the machines, it takes about another 3 minutes. And then to actually run the installation, it takes another 7 minutes. So that's the breakdown of the 13 minutes. So for a 30 node cluster, we can spin that up in about 13 minutes, which is pretty good. Once we have that, we can kind of take a peek into the dashboard, and what we see here are all the different nodes. The nodes have no names, they're not pets. We don't give the nodes names, they're just ephemeral things. So if they go away, we don't care, we just spin another one up and we get a new IP. So these are all listed kind of by their IP, and you can kind of see what's allocated on those machines with the colors that are on the right as far as memory, CPU, and disk. The 10 node cluster, again, I gave it away earlier, but the 10 node Elasticsearch cluster that we spun up here, each of those nodes has 27 gig of memory, and then it also has almost 1 terabyte of disk space. This took about 47 seconds to do this. Even when we do a 30 node cluster, it takes about the same amount of time because they're all done in parallel. They all join the cluster in the same way. And it doesn't really take much more time depending on, the number of nodes doesn't really matter. So once we have the Elastic cluster in place, we can see that our tasks are running. These are the nodes that those got allocated to. So again, we didn't really choose which nodes to put those on. We just said, thank you, Mr. Big Operating System. Go deploy 10 of these things, and it figures that out for us. So the demo that we're going to show here is we've got a partner of ours that shared some data with us. And they basically collect data from mobile app usage anonymously from cell phones. And basically what we have is a whole bunch of CSV files that we wanted to bring into Trinity. Each one of these files contains about 7 million records. We loaded the first 200. I think we had 500 files, but we just loaded the first 200 for the purpose of this demo today. So this has, in one feature service, we have 1.4 billion records in that feature service. And so I don't know if you've ever worked with a 1.4 billion feature service before, but it probably didn't work very well if you've done it before. And so to load this data into Trinity with that 10 node Elastic cluster, we were writing about 72,000 writes per second. So it took us about 5.5, 6 hours to write that data in. We haven't spent any time to optimize this or any of that. So this will be much better over time, but this is just the default of what we've loaded in. Just a note on the data is that seems like a lot of data, but that's about 2% of the population for 3 days. So just to give you a magnitude of the real problems people are trying to solve is, if you were an intel agency or some other type of agency and you actually had access to 100% of the data, that gives you a magnitude of how big this data would be. And those are the types of problems that we're trying to solve with Trinity. So here's a couple dashboards. If you're familiar with Elasticsearch, Kibana is the monitoring interface on top of Elasticsearch where you can go explore things. And this is just a screenshot of the 5 hours where we were loading the data. And you can see that we were loading, at that point in time, 100,000 records per second. And our latency was less than half a millisecond. This is the nodes view inside of Elastic. So after we loaded the data, we still have lots of space on the machines available. And you can see the number of shards and the CPU and everything else that's happening on this. So one of the key aspects of Trinity is that we really need really good instrumentation about what's happening in the cluster. And so how are our services performing? We don't really care how the nodes are performing, we care how our services are performing. So with that, I'm going to hand it over to Suzanne, who's going to kind of walk through an early glimpse of an early form of this.
Great, thanks, Adam.
Assuming I can get my screen up.
There we go. All right, so as Adam said, I'm going to walk you guys through an example of using the task manager of this Trinity project that we're working with, using the safe graph data. This is basically an app that's very much in development. It's got a couple major sections to it, but this is going to be eventually the interface that users would have when they're working with a cluster that is, architected and using this technology. So the application has or will have a monitoring page that'll look something like this, and it'll allow you insight into the various tasks that are running on your cluster. It'll give you information about the CPU load and the memory pressure and the disk space for any one of these tasks. And it'll also give you insight into the nodes that any one of these tasks are running on. This information right now is simulated simply because we are working on connecting up the rest of the interface. But Adam was showing you a bunch of screenshots of the operating system software that's running behind the scenes, and those types of statistics will make their way into this interface. Much like GeoEvent Manager today, if you're familiar with it, there's different components to this overall interface that allow you to manage the sources and the sinks for your data. So those would be like input and output connectors in GeoEvent Manager today. You'll also manage the different big data stores that you can have. You can actually have multiple big data stores in your cluster if you'd like to. And you can also do housekeeping with regard to the data sets that are created, the services that are defined off of them, and so forth. The Analytics tab is where today in GeoEvent, this would be GeoEvent Services. So you would connect inputs to outputs and define processing steps along the way. With the Trinity project, we actually have a concept of real-time analytics and scheduled analytics. So real-time analytics will bring in the streaming data, capture it to the data store, do any other in-stream processing that you need to do. And scheduled analytics will allow you to run batch tools. And we'll return to that more in a moment. And then the System tab is where you'll get to a lot of the underlying housekeeping capabilities, like managing your data schemas, managing the hubs and the brokers that are working on the cluster, and so forth. So this is your management application, basically. Now, under the Data tab, if we just roll back a couple steps, one thing you'll see here is that we have one data source running. This is a simulation of some of that safe graph data that's running in. And we have a real-time analytic that's bringing in that data and writing it to the data store. So the analytics in Trinity will have a task designer interface, somewhat similar to how you design GeoEvent services today, or more generally how you might define processes in Model Builder. It's a visual programming interface where you can connect inputs to different steps and configure different output actions. So a lot of the real-time analytics that you might be familiar with from GeoEvent will make their way into this application. You'll be able to filter events based on attribute or spatial conditions. You'll be able to do field calculations, buffer events, and generally use these tools together to ask more complex questions. In this case, we're just bringing this data in straight to the data store. And much like you may have seen so far this week, and much like you may have experienced with the spatiotemporal big data store in the on-premise software today, when you bring data in and write it to a feature service that's based on that data store, you can basically get a map service that provides on-the-fly aggregation of your large data sets. So here I'm just showing that we can bring in that data in real time. This is all happening on the cluster, and the data store automatically is producing that on-the-fly aggregation map for us. So we'll come back to that again in a moment. Now, behind the scenes of what we're working with, Adam introduced this in the slides, but this is basically the DCOS dashboard of the cluster that we're working on. So as Adam was saying, we have 33 connected nodes here. We have a total of 22 tasks. I'm only using about 39% of my overall CPU capabilities right now on this cluster. If we go to the Services tab, we can see the different components of this that are running. So we have a task running that actually drives the application itself. The management application. We have a real-time task that is taking that safe graph data, pushing it to the data store in real time. And there's other tasks that manage the Elasticsearch, that manage the ingestion of the data, and so forth. Now, going back to this data just for a moment, we are running it in real time here, which would probably be the long-term solution with any implementation that we would do. But as Adam was saying, we also received a bulk load of this data from SafeGraph, so we used a batch task to load this in a large quantity to the big data store all at once. So if we take a look at that, this is basically that 1.5, it's 1.48, 1.5 billion records that represents about 3 days worth of data. It's generally over the course of a week, and the files were not organized by time, but in total we have about 3 days worth. And with the big data store and the aggregation map service that's generated on top of it, we can go ahead and look at more and more refined views of this data as we go. Now, of course, this is reaching back out to that huge data set, and every single time you pan and zoom, it takes that extent, it asks for accounts of the features back, and it just returns the amount of features that are in that data set within the extent and at an appropriate grid scale for your resolution that you're looking at, or your scale. So here you can see these abbreviations are showing you how many observations there are in each of these geohash cells. So we've got 20 million or so here in New York. And I'm just zooming in a little bit to New York so that this will get more refined over the city of in just a second. So the data in this data set is obviously very, very dense, and we can just keep getting closer and closer and seeing the actual population pattern as we get down to the streets of New York City here. The other thing that I want to say as this data comes in is that the aggregation that you're seeing is, of course, completely dynamic. As you get closer and closer with your large data sets, it'll be faster and faster because it's querying less data each time, of course. And even though you're seeing an aggregation, the raw data is still available to you at any particular time. So if I click on this aggregation, I see all the features that were located within the tolerance of that mouse click. So I can get to all the raw feature information here. In this case, we didn't have a lot of attributes with the data because they provided us a pretty streamlined data set. But depending on the attributes that come along with your data, you'll be able to access that even though you're visualizing the map in a more refined and easier to explore way, per se, than drawing all the features individually. These on-the-fly aggregations are also completely relative to whatever query you send to the map. So we're just going to switch over in this case and look at the data over time. So even though we're doing this aggregation, it'll be filtered by time accordingly if we're using it with the time slider. So right now I'm looking at the DC area, and we're just going to play it by hour over the course of a Monday, September 26th. And it's kind of interesting, we're in the wee hours of the morning here from 2 a.m. to 3 a.m. And we can start to see sort of the rush hour pick up in the DC area. From 5 to 6 a.m. we're starting to see focused activity on some of the highways close to the city. We see the congregation of devices downtown, if you will. And as we start to reach the middle of the day, you really start to see the main bulk of activities in downtown DC here, as you might expect. And as we reach the afternoon hours, at least to me, I kind of feel like we do start to see the data spread out, and we start to see people moving away from the downtown area and starting to spread out back into the rest of the area. And then as we enter the evening, it just kind of oscillates back and forth a little bit. But you can imagine the power of data like this to really begin to look at population distribution over the different hours of the day and different areas. The other thing here is that, of course, much like you can filter data by time, you can filter data by attributes. So instead of looking at all of our features that are in this entire data set, we could filter it by the device ID, for example. So this is the pattern of one particular device as it moved around the DC area. We can see concentration of activity in a particular location. Or, for example, another device here, which looks like a commuter who spends a lot of time up in Baltimore and also down in DC and goes back and forth between the two. So the aggregation is completely flexible in terms of what queries you send against it. In this case also, we're looking at the raw count of observations, but you can also run these aggregations with statistics. So you could look at different patterns in the data depending on the attributes that you have. The other thing before we shift back over into slides for a deeper dive is these scheduled analytics are one of the, I would say, the main differentiators too with the way that this architecture is going to work. Today, we have real-time analytics that operate continuously with GeoEvent. Here, obviously, they'll be able to operate at a more massive scale. And we're also going to have the capability to run batch analytics on a recurring basis. And this framework will also allow you to stitch together multiple tools, much like you can with a GeoEvent real-time workflow today. you'll be able to stitch together multiple batch analysis tools to form a longer workflow and execute that on a recurring basis. Our plans for this eventually are to have all of the geoanalytics tools in this application and be able to run them on this framework. So for example, we've already moved a couple of these over, like the join features tool and reconstruct tracks, for example. And you'll actually be able to pipeline them and build longer workflows. And then the other key aspect of this is that we'll have an ability for you to schedule these tasks. So by default, you might run a batch task one time, but you'll also be able to assign these tasks so that they run every so often, because the idea being that if you have real-time data coming in, you might want to run an aggregate points or do some sort of join analysis, and you don't necessarily want to run that in real time, but you might want to run it every 5 minutes or so and create an analytical product that automatically updates regularly. And that's what this basically will allow you to do. This is very much still in development, so I'm not going to run this particular task right now. We have another task here, which is just taking the data, filtering it down for a device ID, and reconstructing the tracks. So I'm going to go ahead and run this particular batch job. Right now I'm just running it ad hoc, so I'm running it one time. And it could, of course, be scheduled. But as we come back over to our DCOS interface, we can see that that job has now been added to the cluster and it's running. And when it completes, it'll go into a completed mode. If I had it scheduled to run periodically, I can see that schedule in this interface. And since we just finished this task, we can go ahead to our directory and see that we've created this new set of features. So I'm going to go ahead and add that back into our map. And in this case, I was running the reconstruct tracks on the device that you're seeing in the map here. So I can go ahead and add this to the map, and we can see those reconstructed tracks. Now, granted, we have a couple days of data here, and it's scattered data that actually existed over 7 days. So there's some jumps in the tracks as we had gaps in the data. If we load the rest of the data set, then we'll be able to have a more clear result there. But these will be very powerful capabilities in the long run for data like this, for example, to do traffic analysis and different traffic levels at different times of day. So some interesting R&D that we're working on, and hopefully by UC we'll be able to show a longer process working in this architecture. So I think that's about all I kind of wanted to go through with you guys, so I'll go ahead and turn it back over to Adam.
All right, thanks, Suzanne. So hopefully it gives you more of a tangible view into what Trinity is. I'm going to take a little bit of a deeper dive into what's actually happening in Trinity, and then I'll take it up a level and we can do some Q&A. So as far as the quadrants of focus that we have, we typically focus on being able to ingest data, being able to analyze data both in the stream as well as after the fact through batch analytics, to store these data and to visualize them. Our benchmark for 10.5 has been in the arena of thousands on the left side and millions on the right side. So what Trinity allows us to do is to take that to a magnitude different, where we're focusing on millions, or we could actually scale up even further than that if we needed to, into the billions on the right. And so the way we can do this is through what I mentioned before. We've decomposed a lot of our products that we have today into lightweight services that we can run very quickly on this environment. And so we've decomposed what GeoEvent is into sources and hubs and real-time analytic tasks, or what were GeoEvent services before. We've decomposed the spatial temporal big data store. It was kind of actually written that way in the first place at 10.4 with this in mind. Geoanalytics was also written that way with this in mind as well, so it's been fairly easy to pull those things out. What's on the top right is the start of some decomposition of ArcGIS Enterprise, where we have the brown map application task, or what's known as a lightweight map and feature service. So we can run feature services and map services inside of this environment without having to run a heavyweight ArcGIS server on each of those machines. We can spin those up very quickly, and we've decomposed that out of the server stack. So there'll be more work going on in the future to decompose even further. But this is basically what the Trinity environment looks like. We're making use of Mesos and DCOS, as we mentioned before, to operate the entire environment and treat it as one big operating system. We're using Kafka for our sources and our hubs. We're using Spark for our real-time analytics and for our batch analytics, and Elasticsearch for our big data store. And that's kind of our big picture. So if we look at the actual containers that we have that run inside of Trinity today, these are the different containers that we have. And it's probably like super small font at the bottom, so I apologize for that. I didn't realize we were going to have tiny screens in this room. But the sources are basically a lightweight geo-event input. The event hubs are lightweight geo-event hubs, which are internal details that you don't worry about today. The real-time analytic tasks are like a lightweight geo-event service. And then the batch analytics are lightweight geo-analytics jobs that run. And then as I mentioned before, the map service is a lightweight map and feature service that runs. And so this is the containerized environment that we run. And so when we start to deploy these into an environment, we establish a big data store cluster, we run map and feature services. So the cool thing here is we can actually scale out map and feature services really large too. So if you're a weather provider and you have hundreds of thousands of concurrent clients that connect to the system, you can scale out your map and feature server layer to be really large if that's your use case. So you could have lots of brown tasks running in this environment. And so that's very easy to do, just like it's very easy to scale out your storage cluster. And so every one of these microservices can be scaled out as big as you need them to be scaled out. You can also run your batch analytics, but a bit more detail on the batch analytics is we've got a sub-project of Trinity called Bonsai. So Bonsai like the big wave in Hawaii, but I'm taking liberal application of that to be bonsai like the Lion King animal. So if you have kids, you know what I'm talking about. If you don't, then I'm sorry. But it's a cute animal on the top of the screen at least. So Project Bonsai was basically taking geoanalytics and allowing it, instead of just running one tool at a time, to pipeline those together and then also allow scheduled aspects to that. So I could say, run this reconstruct tracks every 5 minutes and produce new results, or append to an existing feature service with new results. And that's what Project Bonsai is about. So Bonsai basically allows us to run these geoanalytic jobs in a really lightweight way where I could consume all of the cores that are available, or I could consume a portion of the cores and run multiple of these concurrently. And so it's really up to a user of Trinity to configure this however they see fit. So if you want your jobs to run faster, you can consume more resources. If you want to run multiple concurrent, then it uses whatever resources are available. The pictures on here are showing it all at the bottom, running on the same node as where the data is. That's where it's optimal because we don't have to move data across the nodes to do the analysis. But if it got full on the bottom, we could certainly run green things in other nodes. It's just going to have to move the data across the nodes, which is slightly slower. It's still really quick as well, though. So that's Project Bonsai. And so we denote the analytics space there for batch analytics, and recurring analytics is the green area there, but there's actually nothing that's running there. It's just idle and blue space waiting for geoanalytics jobs to be run. So then we run our hubs, and then we run our real-time analytic tasks, as we mentioned before, and then our sources. And this is kind of what makes up the whole environment for Trinity. What's actually cool, though, is that we can actually run the ArcGIS Enterprise outside of Trinity if we want to, or we could actually run it inside of Trinity, where we actually run the portal, the hosting server, the relational data store, all the other things. Actually, what we need to run a Trinity is just the portal. We really don't need the hosting server because we have our own lightweight map and feature services, and since we don't need the hosting server, we don't need the relational data store as well. So the only thing we're really running in Trinity is the portal, and that's to make Trinity look like a portal. So there's 30 nodes in this cluster, but a user of that portal would never know that there's 10 nodes doing storage and other things like that. All they know is that there's a feature service that has 1 billion records in it, and they can access that and do things with that outside. And it's performant, you can query it, you can do things with it. And so the whole portal to portal collaboration story becomes really important here, because I could have a portal that's really focused on real time and big data, and I could integrate that with my other portals that I have within my organization. And so I can share this data by reference. I can do other things in the other portals that I collaborate with. And so that is a big aspect of this as well. So this is just a more detailed look under the hood of the technology that we're using for these things. And to run a Trinity environment, we have some meta nodes that basically take care of scheduling all the resources and the tasks that run on there. And so those are just kind of overhead nodes that we have inside of Trinity to do this. So our initial plan for Trinity is to really target like 4 or 5 customers in 2017 as a managed service where we would deliver this and manage the environment for the customer. But we would also bring along professional services folks to deploy this as a project. Our goal for this in 2017 is really to cut our teeth with this technology, make sure we get it right. Those customers that we're selecting are really big volume, big velocity customers that we're picking too. And so then we would take this architecture and actually make it available as ArcGIS Online software as a service offering, so that if you wanted to go do these things, you could go create a feed on ArcGIS Online, or you could go create a continuous analytic on ArcGIS Online that made use of these same capabilities, and you could start to do that. So expect that work to kind of come, post 2017, but that's really the bigger plan for what this architecture is going to do. So that's kind of the next steps. The first step is to deploy these using our Esri Managed Cloud Services folks. These can be deployed to Amazon or Azure, but they also could be deployed on-premise for certain needs. So if it's a closed environment with no access to the internet, or it's some other type of environment, we can deploy this into any of those environments. It typically comes along with the professional services project. I'm only talking about like the initial offering of this. And it's still called Project Trinity because we don't even have a product name yet. So we're kind of sharing this early with you. We have 3 or 4 product names in mind, but I don't think we're at liberty to share them at this point. It would be great to do that, because then you can tell us which one you like. But that's it. And then the other big thing here, which is slightly different than other ArcGIS Online services, is the ability to deploy these close to where your things are. So the whole premise of Trinity is to give you an IoT foundation to do geospatial reasoning in your IoT. And if you're deploying this and you're a customer in Japan, you don't want to deploy this in Oregon. It doesn't make sense. So we have the ability to deploy Trinities to any number of regions around the world on Azure or Amazon on public clouds, or if there's a local provider like Do in Dubai or other places like that, we can deploy to those local cloud providers as well. This is just some of the availability of the different providers. Azure has been working with us very heavily as well to prove this architecture out as well, and so we should definitely give them accreditation here as well. A lot of our big clusters, our 30 or 100 node clusters that we build for these environments are mostly on Azure, but we support Amazon just as well. There's nothing native that we're using on Azure. There's nothing native we're using on Amazon. So we're completely deployable to any environment. It's really a paradigm shift, kind of like what Java was in the mid-90s, if you're around at that time, of write once anywhere, even though it really didn't work until many years later. There's the same kind of paradigm shift here, where we're writing these applications once and we can deploy to any type of cloud provider or on-premise system. So I'm just going to summarize here and leave plenty of time for questions, because there's probably lots. But 10.5, we're kind of showing you the latest and greatest R&D stuff that we're doing. We're showing you this early because we want to get some of your feedback on this. But we have a very functional system at 10.5 today that's very capable. Satisfies probably 95% of our customers' use cases today. We're really targeting Trinity at the other 5% of customers and customers that we're expecting to emerge over the years as more and more sensors come online and the performance requirements become higher and higher for things. GeoEvent Server can be used today to do a lot of this real-time GIS. The big data store is a really good solution. In fact, the big data store that's on-premise is the same big data store we're deploying in Trinity. There's no code differences at all. And geoanalytics is very functional for doing batch analysis. We're leveraging the same tools, the same algorithms inside of Trinity to do those. We're just adding the pipelining and the recurrence capability inside of Trinity. A lot of those capabilities will find their way back into 10.6 releases and other things as well. So we're using Trinity as an innovation ground where we can bring ideas back into the on-premise software as well. So it's not exclusive that we're just innovating in Trinity. We're innovating in Trinity. And if you came to the WebGL session earlier, or you come to the Big Data Store session tomorrow, you'll see a on-the-fly space-time cube analytics and other things that we're doing. And so those were all born out of the Trinity effort, and we're bringing those back into on-premise 10.6 deployments. So we're sharing this early. The target for Trinity is really for customers that need massive scale things in the 2017 timeframe where we don't have other solutions and where they would never be able to use our on-premise software due to the performance limitations, even though they work for 95% of our customers. With that, there's a number of other sessions. I would highly suggest if you're interested in the Big Data Store, there's a session tomorrow at 4. That'll be a really good session. We're going to go into detail about how we do spatial indexing, how we do the aggregations, some of the space-time cube stuff I was mentioning before we'll show there. And then there's a best practice session on Geo Event Server that won't just be Geo Event Server. We'll be talking about the big data store best practices and other things in that session as well. So those are two, if you're making heavy use of this, that you should probably plan to attend. With that, we'll open it up. We have about 10 minutes for any questions or feedback or comments you guys have. You guys like this stuff? Is it cool? Yeah? Yes, sir?
Yeah, is each class of your nodes capable of reading and writing to object storage, or are you relying on some more localized storage within those containers?
Yeah, good question. So the question is each of the nodes in that cluster does it have same access to the object storage, or is there ephemeral storage or other things available to those nodes? So it's really up to you, the project team that's configuring Trinity, to define that. We're pretty flexible. So the way this cluster was set up is we had homogeneous nodes across the entire cluster. We can actually have heterogeneous nodes if we want. So we could say these nodes are for storage, and we can tag them with storage. And when we say run a spatial temporal data store, we can say only run on a node that's tagged with storage. And so we can kind of pin it to those classes of machines. And those big data store, or those storage nodes, can actually have attached local SSD drives, or we could attach other types of premium storage to them. And so that's what we're using as attached premium storage inside of the different Amazon or Azure environments. They certainly have access to object stores as well. So if you want to use Azure Blob Storage, or you want to use S3 inside of those environments, we can do that as well. That's not typically what the storage would be for the spatial temporal data store, though. It's much more optimized to use a local SSD. So that's how we configure that. Any other questions or feedback? Yes?
What's the difference between bigger store and SQL server? I know SQL server will not be able to handle meetings record. I have meetings record in SQL server. It's very slow to just query.
Yep.
So I don't know what's the difference between the better store and SQL server.
So the question is, what's the difference between the spatial temporal data store and SQL Server? So I'm trying to figure out where to start with that. SQL Server is a relational database. That's the first difference. And the spatial temporal data store is based on Elasticsearch, which is a NoSQL database. And so SQL Server is only vertically scalable. So you can only allocate more cores if you have a bigger machine to do that. So you have to scale up. Versus with spatial temporal data store and a NoSQL database in general, you scale out by adding more nodes to that. So it's more flexible in how big it can scale out. The other thing is the spatial temporal data store is indexing all kinds of things. So we're indexing the ability to aggregate by hexagon, or aggregate by square, or aggregate by a different projection system, or all of those things. So that when you access the data, it's a super fast query that would come back. Did that answer your question?
So you have 10 servers collected for the bigger data.
Yep.
Let's see, you basically, like I said, you basically split the bigger data into pieces, storage pieces on a different node.
That's right. Yeah, so the comment is in the big data store, when we have 10 nodes, we are partitioning the data to different nodes in the cluster. So if there's 10 nodes and we have the configuration that we're going to write to one node and we're going to replicate to one other node, we would write to a primary node and we would replicate to another node. So we have a technique for how we actually partition the data. We do it by what's called a track ID. So if your phone is reporting into Trinity, your phone will always go to the same primary node, so that when we do reconstruct tracks on a specific track, it's super fast because all the data is in one place. So there's different sharding techniques or different partitioning techniques that you can do. That's our default. We haven't made it pluggable at this point, but that's how we partition the data. And so that's how we can store huge volumes of data, because we're not storing the same data on every node. We're storing just part of the data on each of the nodes, but there's replicas across the nodes as well, so that if there's a failure, it can take over and not lose any of the data.
So that's the reason why bigger data store is faster than SQL Server.
So the question is that the reason why it's faster than SQL Server? So that and a number of other reasons, being that we have 10 nodes with 8 or 16 cores each and 28 gig of RAM each that can respond to that, whereas SQL Server has one node with 8 cores and 28 gigs of RAM. So it can also keep stuff hot in RAM that's been accessed recently too. So like when Suzanne was doing the zoom-ins and stuff, we're leveraging the hot data aspect of it too, because it's not going back to disk every time. So it's keeping some of that data hot so that it can just aggregate new stuff and calculate those on the fly. Question?
Maybe I don't understand very well, but Project Trinity behaves like a GIS server, maybe analytics and so on. It looks like a GIS server, but there is no a single proper GIS installation inside the whole system. I mean, there is a portal, if I understand, but on the core there is only Spatial, Elasticsearch, and so on. So we don't have any type of ArcGIS proper installation on the core.
So the comment is, it doesn't look like you have any ArcGIS server stuff running inside of Trinity. Is that the case? So we have a portal that's making the Trinity cluster look like a portal. So you can use the same security, you can share the same way you would share between a portal and other things. Within Trinity, we have a number of different tasks that we can run. So one of those tasks is a lightweight map and feature service. So when Suzanne kind of went into the REST interface, it looked like server, but it wasn't server. It was a lightweight map and feature service that was returning that response. So we've decomposed what is server into the pieces that we need to run Trinity.
What's a lightweight feature server?
So the question is, what's a lightweight map and feature server? So we took the feature server and basically had a fully functional feature server that we can run in like a 100 megabyte jar file instead of installing a heavyweight ArcGIS server. So I can go deploy 20 of those across the cluster in 5 seconds, as opposed to installing ArcGIS server on multiple machines over multiple minutes. So that's what's lightweight about it, is it's very small, it's only meant for that specific. This is the whole premise of what a microservice is. So it does one thing and it does it well. It does map and feature service. If you wanted to do GP, there would be a different GP job runner that would be running somewhere else. So it doesn't do that. It's only meant for its sole purpose of what that service is. Yeah. Good question. Yes? So the question is, what's the timeline for when this becomes available on the market? So we're having a holistic lab in mid-May. That's where we transition from our alpha stage to our beta stage, and then we're planning to GA this in the late Q3 timeframe. When we QA it in the late Q3 timeframe, it's going to be GA'd as a managed service offering that comes along with professional services. And we're really only trying to target, a small number of customers to cut our teeth with it, so that we can then take this architecture and make it a SaaS offering on ArcGIS Online. So that's our technique for it. But if you're interested, certainly talk to us and we can. Yeah. I'm sorry?
Yeah, we have an island.
Yeah,
Come find us.
There's a real-time
and
NGO event island. Yeah. Any other comments or questions? Yeah. Yes.
So once we eventually get it on, how is that going to work? The product
So the question is, when we go on-prem, how's that going to look like? So a lot of our on-prem customers actually have private clouds. So like in the Intel and the defense space, which is where a lot of this kind of applies, they have environments like C2S, and so we're certified, or we're in the process of certifying on C2S, where we can run inside that type of environment. So I think that probably answers your question. Okay, great. We'll stick around afterwards. Thank you for your time.
Thank you.